For more physics-related videos, please subscribe. Welcome to Stellar Physics 4e. In this video, I'm going to cover the maximum neutron star mass. I already covered this in a previous video, Stellar Physics 3d, but in this one, I'm going to do it from a slightly different point of view, specifically from the point of view of energy and stability. As with all the other videos in this chapter, the physics in this video will be heavily dependent on the results found in Chapter 3, so it would be good to be familiar with that physics before you move on. I rated the physics in this video as advanced because it contains some results from general relativity. Let's start off by going over what a neutron star is. You may recall that during the main sequence phase, a star is fusing hydrogen into helium. When the core runs out of hydrogen, it goes on to fusing helium into carbon. When the core runs out of carbon, we found out in the previous video, when we looked at the Chandrasekhar limit, that if the star is less than about 10 solar masses, it will not be hot enough to go on to fusing carbon, and you will get a white dwarf. If, on the other hand, the star is greater than about 10 solar masses, the next nuclear burning phase is to fuse carbon. Now, there's actually a few different things carbon can fuse into, so it gets a little more complicated at this point, but you're fusing two carbons into something else. At a slightly higher temperature, you'll get hot enough to fuse oxygen. And you keep going on like this, fusing heavier and heavier elements as the temperature increases until you get all the way to iron. So in this overly simplified schematic, you'll have shells of sequentially heavier elements as you go from the outside towards the core, essentially representing each nuclear phase corresponding to a higher temperature. Now in reality, it's not like each shell is only fusing one thing. These shells are just representing the dominant nuclear burning process. Once you get to iron, you'll actually have an iron-nickel core, but at that point, you can't fuse anymore, because in order to make elements higher than iron and nickel, you need to put energy into the nuclei to make them, rather than the nuclei releasing energy when they fuse. So at this point, nuclear fusion stops, and there's nothing to push back against gravity, and the star will collapse. And this will result in a core collapse supernova. The details of a supernova are rather complicated, and I'll leave that for a separate video. What's relevant here is that if the star is less than about 25 solar masses or so, the supernova will leave behind a remnant called a neutron star. If it's greater than about 25 solar masses, it'll leave behind a black hole. So what is a neutron star? Well, it's pretty much exactly what it sounds like. It's a gravitationally bound object of about a solar mass that's entirely made up of neutrons. Now, the neutron star is supported against gravity by neutron degenerate pressure. This is exactly like the white dwarf, except in the white dwarf, the pressure came from degenerate electrons. And in this video, we're going to try to find what is the maximum mass a neutron star can have. Let's start off by reviewing what we found in Stellar Physics 3d, when I first covered the maximum neutron star mass. In this video, I used the TOV equation. TOV stands for Tolman, Oppenheimer, and Volkov, and this equation is the general relativistic version of the hydrostatic equilibrium equation in Newtonian mechanics. In Stellar Physics 3d, we solve this equation assuming a constant density. And we found that under such conditions, the central pressure will go to infinity if the metric deviation, which is this quantity 2gm over rc squared, goes to 8/9. Meaning that if the metric deviation is 8/9, there is no amount of pressure that can support the star and it will collapse. We then guessed that the density should be roughly nuclear density, and that led to a maximum mass of about 4 solar masses, which is likely a little bit high as the largest neutron stars observed are a little over 2 solar masses. The main problem with this method is that we didn't actually know what the density was, and we had to guess it. So since this method did not actually give us enough information to find the maximum mass, let's try a different method. And this is called the TOV limit, named after the same three guys. The TOV limit is basically the same thing as the Chandrasekhar limit, except instead of using relativistic and degenerate electrons, we're going to use relativistic and degenerate neutrons. The Chandrasekhar limit I covered in the previous video, Stellar Physics 4d, and that is the maximum mass of a white dwarf. So for the TOV limit, we're going to follow the same procedure that we followed in the Chandrasekhar limit. Since I already covered it, I'm going to go over it rather quickly. In Stellar Physics 4d, we found that the binding energy of a white dwarf was proportional to 1 over the radius of the star and depended on the number of electrons. So n here is the number of electrons. This term is the Newtonian gravitational potential energy, and this term is the internal energy. I then argued that the star will go unstable when the energy was about 0, which gave us a condition for the critical number of electrons at instability. We then said that the mass of the star would be roughly the number of electrons times the mass of a proton, and this gave us a maximum mass of about 2 solar masses. Then we found that the critical radius would be about the cube root of the number of electrons times the Compton wavelength of an electron, and this gave us a radius of about the radius of the Earth. Now, for the TOV limit, we just replace electrons with neutrons. But notice that in the case of the Chandrasekhar limit, n critical does not depend on anything related to electrons. So the fact that we use electrons is actually irrelevant. So this will hold whether we use electrons or neutrons. And similarly, the critical mass also does not depend on anything related to electrons. So we expect that the maximum mass of a neutron star will also be about 2 solar masses. The critical radius does depend on the electron mass since it depends on the Compton wavelength. So instead of the electron Compton wavelength, we use the neutron Compton wavelength, and this gives us a critical radius of about 3 kilometers. Unfortunately, there's a problem here. If we take this mass and radius, we get a metric deviation of about 2, and the metric deviation has to be less than 1. At 1, you have a black hole. So this is not actually physically possible. But we can say this is a rough estimate. 2 is not that far off from 1. If we do this calculation more carefully, maybe this metric deviation will drop below 1. But unfortunately, the problem doesn't end there. This binding energy we used is the Newtonian binding energy. And Newtonian gravity only holds if the metric deviation is not only less than 1, but very small. So it has to be a lot less than 1. Well, before we throw this method away, let's at least calculate it exactly and see what the metric deviation comes out to be. This calculation I also went over in Stellar Physics 4D when I did the Chandrasekhar limit. So again, I'm not going to repeat it. If you want to see it, you can watch that video. So let's summarize what we found in that video for white dwarfs, and then see what the result would be for a neutron star. For the Chandrasekhar limit, we found that the maximum mass is equal to 1.4 solar masses times this quantity which I wrote as 2 times Ye squared. Ye, if you recall, is the electron fraction. It's the number of electrons divided by the number of baryons. And I wrote it as 2Ye because we expect Ye to be very close to 1/2. We also found the central density at the point of instability. And I've written the critical density in this somewhat strange way to explicitly show where any dependence on electrons shows up in this result, because ultimately we want to replace the electrons with neutrons. Then we found the critical radius for a white dwarf. So now for a neutron star, the calculation is exactly the same, but we replace electrons with neutrons. So we substitute the neutron mass for an electron mass, and the mass of a neutron is basically the mass of a proton. So this ratio me over mp becomes 1, and we set Ye to 1. Why is Ye 1? Remember what Ye is. Ye is the number of electrons per baryon. Or the relevant way to think about it in this case, it's the number of degenerate relativistic particles per baryon. Well, when we're in the neutron star case, the degenerate relativistic particles are neutrons. And all of the baryons are neutrons. So the number of neutrons per neutron is 1. Plugging in the numbers, we get that the maximum mass is almost 6 solar masses. The critical density is about 10 to the 16 grams per cubic centimeter, and the critical radius is about 18 kilometers. Now, if we plug into the metric deviation, we get a number that's a little less than 1. So this is actually possible. And we expect the metric deviation to be somewhere near 9/8. So this seems to be plausible. Unfortunately, there's a hidden problem here. When we did this derivation, we assumed a polytrope profile for the density. If you don't know what a polytrope is, you can watch my video on polytropes, Stellar Physics 3B, but essentially what it is the radial density profile of the star. So it's how the density changes with radius. And we use an n equals 3 polytrope because for relativistic material, it turns out that n equals 3. The problem is, for an n equals 3 polytrope, the maximum metric deviation is not at the surface of the star, it's about halfway out. And it turns out to be about twice the metric deviation of the star. So if at the surface of the star we have a metric deviation of almost 1, well, somewhere inside the star, the metric deviation is going to be close to 2. So this actually doesn't work. We also have the problem that this method uses Newtonian gravity, so it assumes the metric deviation is much less than 1. This problem with the metric deviation is just telling us that we cannot use the Newtonian gravitational binding energy. Instead, we have to use the binding energy that corresponds to general relativity. I covered the general relativistic binding energy in Stellar Physics 3F. The gravitational binding energy in general relativity is defined as the total energy of the star minus the rest mass energy of the star. So m here is what is sometimes called the gravitational mass of the star. It is the total mass energy content of the star. This is the mass that determines orbits of objects around the star. So this is the mass that we measure. M naught is just the total number of baryons times the rest mass of a baryon. This quantity cannot be measured because we have no experiment that can count up all of the particles in a star so we can then multiply by their rest mass. In Stellar Physics 3D, we showed that under Schwarzschild geometry, the rest mass is equal to this quantity here. We'll come back to this in a little bit. First, in order to even do this integral, you need to come up with an equation of state for a neutron star. And the problem here is the equation of state of a neutron star is unknown. In fact, this is kind of the holy grail of astrophysics. If you're finding this video interesting so far, please like and subscribe if you haven't already, and consider sharing with a few friends. Well, one thing we do know is that a neutron star is almost certainly made up of degenerate neutrons. So let's start with that. In Stellar Physics 4C, I covered the thermodynamics of degenerate matter. And in that video, we found an expression for the rest mass density of degenerate matter, where G is the degeneracy. This is just the number of particles you can put in a given energy state. For electrons, G was 2, because it had a magnetic moment that could either be pointing up or down, and that's the same case for neutrons. X is what's sometimes called the relativistic parameter, and it's the Fermi momentum divided by the mass of the particle. If the Fermi momentum is much greater than the mass, then you have relativistic particles. If it's much less, you have non-relativistic particles. And lambda c, again, is the Compton wavelength of the particle. We also found an expression for the total energy density of degenerate matter, which can be rewritten as the rest mass density times c squared times this factor 1 plus epsilon, where epsilon is the internal energy per unit rest mass. And finally, we also found an expression for the degeneracy pressure. Now, since we don't know the equation of state of a neutron star, let's just start with the simplest case. Let's assume the rest mass density is constant. Well, the only variable in this equation is x. Everything else is just a constant. So if the rest mass density is constant, then x has to be constant. And if x is constant, the energy density also has to be constant, as it only depends on x as well. And similarly, if x is constant, the pressure also has to be constant. But this is a problem, because this violates the TOV equation. Now in Stellar Physics 3D, when I first went over the neutron star mass limit, I assumed a constant density and then solved this equation. But I didn't assume degenerate matter. So it would appear that that was okay. But actually, if you think about it, even in that case, assuming constant density has some problems. So let's just plow forward and keep this equation of state and kind of shove under the rug this problem with it violating the TOV equation. Okay, now that we have an equation of state, we can move forward and calculate the binding energy assuming general relativity. Now, just to clarify here, because we have two definitions of mass, the gravitational mass and the rest mass, m of r in this integral is the enclosed gravitational mass at a given radius. And that is equal to the total energy density integrated over the coordinate volume. This integral is in fact integrating over the proper volume. And that's where this factor in the denominator of this square root of 1 minus the metric deviation comes from. That's correcting for the difference between the proper volume and the coordinate volume. The proper volume is the locally measured volume. Remember that space-time is curved, so different observers measure different distances. Since we're assuming constant density, m of r just becomes the density times the coordinate volume. Now we have here rho naught instead of rho. Remember that rho naught is the rest mass density, and rho is the total mass energy density. In the previous slide, we saw how rho naught and rho were related. They were related by this factor of 1 plus epsilon. Recall what epsilon is. It's the energy density per unit rest mass. And in our case, it's constant because both rho naught and rho are constant. So it's going to pull out of the integral. Now in this case, under the assumption of constant density, this integral turns out to be solvable analytically. I'm not going to do it, but it turns out that when you actually do this integral, you get the following rather messy looking expression for the total binding energy of the star, where z is defined as the square root of the metric deviation at the surface of the star. Now I don't want to have to keep writing this messy expression every time, so I'm going to rewrite it as mc squared times 1 minus 4 times a function g of z divided by a function f of x, where g of z is this function in the numerator divided by z cubed, and f of x is this function in the denominator divided by x cubed. This function of x here, by the way, just comes from this 1 plus epsilon naught, or this rho divided by 1 plus epsilon naught. Since we have constant density, the metric deviation can be rewritten in terms of the mass and the density instead of the mass and the radius, and in that case, we have z equals the following expression. So z will depend on both x and the gravitational mass of the star. From this expression, we can get the derivative of z with respect to x. The problem with this expression is that it's dependent on the mass, and the mass is just the total energy of the star, and that can vary. What is constant is the rest mass energy of the star, because it's just counting up the total number of neutrons in the star and multiplying by their rest mass. So it would make more sense to rewrite this energy in terms of the rest mass. Now remember that this entire expression equals the gravitational mass minus the rest mass. So this second term here, mc squared times 4g over f, that's the rest mass. So we can easily rewrite this equation in terms of the rest mass, and now it's the total energy of the star that depends on f and g. So this term, the rest mass times c squared times f divided by 4g, that's the total energy of the star. Now that we know what the energy is, we can solve for equilibrium and stability, which I covered in Stellar Physics 3G as well as Stellar Physics 3E. Equilibrium is found by minimizing the binding energy, which amounts to minimizing the mass because this second term is just the rest mass and that's a constant. So we can minimize m, keeping in mind that m depends on z and x, and we have this expression for the derivative of z with respect to x. Instability sets in when the second derivative evaluated at equilibrium is equal to 0. Now you can sit down and do both of these derivatives and set them equal to 0 and try to solve for the mass, but it is a giant mess, and you will not be able to solve this analytically. But we can solve it numerically, and when we do that, we find that x critical is about 0.6 and z critical is about 0.62. This results in a maximum mass of about 0.85 solar masses, a critical radius of about 6.5 kilometers, and a critical metric deviation of about 0.38. Now, how does this compare to observation? Well, the largest observed neutron stars are a little over 2 solar masses, and the smallest observed neutron stars are over 1 solar mass. So this maximum mass, even though it's in the ballpark, is way too low. It's so low that every neutron star that's ever been observed is larger than this maximum mass. So obviously that can't be right. The critical radius, it turns out, is not too bad. Typically neutron stars have a radius of about 10 kilometers. And the metric deviation at instability is pretty low. Remember that we expect it to be in the ballpark of 8/9. So this method, while it gets not horribly unreasonable numbers, clearly doesn't work. And why doesn't it work? Well, obviously because we used an equation of state that's not consistent with the TOV equation. But like I said, we don't know what the proper equation of state is. In summary, We've used 3 different methods to find the maximum mass of a neutron star. So let's recap the results of those 3 methods. We first have the TOV limit, and the main problem with this method was that the metric deviation was too large. We started off with a binding energy that only held in the case of a very small metric deviation, and even this 0.94 value for the metric deviation at the surface turned out to be problematic because it implied that inside the star the metric deviation was almost 2. Another problem that I didn't mention with this method is that it assumes hyperrelativistic equation of state. And probably the neutrons in a neutron star are not hyperrelativistic. They're probably mildly relativistic, meaning that the relativistic parameter when looking at degenerate matter is probably somewhere around 1. Then we have the method we used in stellar physics 3D, which was to solve the TOV equation assuming a constant density, and this gave us a condition for instability of the metric deviation being equal to 8/9. If we then assumed a density of about nuclear density, we got a maximum mass of about 4 solar masses and a critical radius of 13 kilometers. The problem with this method is we had to guess what the density is. And finally, we tried to find the maximum neutron star mass using the general relativistic definition of binding energy and assuming a degenerate and constant density for our equation of state. The main problem with this method was it was not consistent with the TOV equation. And actually, as I mentioned earlier, it turns out that this second method was also not really consistent with the TOV equation. So in summary, all of these 3 methods gave us results that are somewhat similar to one another, but they all have their own sets of problems. Now the real question is, how do these results match up against observation? Well, as I mentioned earlier, neutron star masses range from about 1 to 2.5 solar masses, and they have a radius of about 10 kilometers. So these 3 methods are not horrible, but they're not great either. Now there are other equation of states people have used, and they all get results that are more or less similar to the results we found here, as well as all having their own sets of problems. All this is to say that the neutron star equation of state is unknown. So if you're looking for an interesting problem to work on in astrophysics, this is a really good one. If you enjoyed this video, please like and subscribe if you haven't already. In the next video, I'm going to go over the electron-positron pair instability. If that sounds like an interesting topic to you, be sure to hit the bell to be notified when this video comes out. Thanks for watching.